All right, we've been talking about all kinds of different variables in the atmosphere up until now, including temperature and pressure and density. Well, this week we're going to talk about moisture. Uh, I think every one of us is kind of interested in moisture just because we like to know when it's going to rain on us or snow on us, or is it going to be a cloudy day or a sunny day? All things pretty much that most of us really are kind of concerned about, especially how much of those bouts might happen. Yeah, I know if I wanted to go to the beach and I wanted to sit out in the sunshine, I don't want to see a whole lot of clouds around that day. Of course, it's 95 degrees and real hot and humid. Maybe I do want some clouds. So I started off here by showing you a satellite picture of moisture. This moisture, the greener they are, the more moist the air is. They're kind of showing you where moisture is coming from. So if I were out on the West Coast, for example, and a wonderful view of the West Coast that went out more in the Pacific, you can see moisture just streaming in up here in the area from that area. Precip moving into the mountains there and all causing all kind of rain, I bet. Now, if I was up in the Dakotas, Minnesota, where's that moisture coming from? Well, guess what? It is actually coming out of the Gulf of Mexico. You can go down here and see this plume of moisture working its way up all the way in to that area. And finally, off the East Coast, this is what's left of Ophelia, which gave me plenty of rain and wind. And here is the moisture that helped to feed it initially. Now it's kind of separated away from it. It's out over the Atlantic, but guess what? If I go down here a little bit, I can see that moisture is originated in the Caribbean, the southern tropics of the Atlantic. So again, a lot of moisture. Interestingly, if you moisture out of the atmosphere everywhere, you would basically get 1 inch of water all over the world. So think about that for a second. And I want you to think about my house the other day had a little bit over 2 inches of rain. Some areas around me had 6 and 7 inches of rain. The atmosphere can't hold 6 or 7 inches of water in it. The most typical at any maximum time is about 2 to 2.5 inches in literally tropical systems that originate in the tropics. Well, if that's the case, then how did they get 7 inches of rain? They got it because the winds are blowing the moisture up from moisture source regions such as the tropics into my area yesterday and dumping, allowing the precipitation to occur very heavily. So you don't need in one individual location a whole bunch of moisture if the moisture is being advected, and advection is a huge part of how much moisture you're going to get. One of the key points every meteorologist looks at is where is the moisture from this low pressure system coming from? If I have a low that's moving across Canada, for example, and dropping southeast, there's not a lot of moisture up there. So there's not going to be a lot of precip with that low pressure system. However, if I have a low pressure originates along the Gulf Stream on the East Coast, well, yeah, there's a lot of moisture out there. Or a big low that moves across the middle section of the country, up from the Gulf of Mexico. And sometimes it even goes all the way into the tropical Pacific. As you can see here, there's some moisture being fed in from that direction as well. So moisture, knowing where the moisture source is key here. So I wanted to just look yesterday. This is where Ophelia was yesterday morning. And there was a lot of moisture around. Notice to the west of it, these are dew points, the bottom left number. We've talked about that. Dew points are a measure of moisture. The higher the number, the higher the amount of moisture. The lower the number, the lower the amount of moisture. Well, dew points in the 50s over here, dew points in the 70s on this side. 73, 73, 73 up here. So there is a lot of moisture to the east coming across the Carolinas. And guess what? Fronts cause rising motion. So the air lifted, cooled, and that when it cools, saturation occurs, clouds occur, and rain occur. And you can see here 3-star rain in this area. So moderate, and some places we're getting heavy rain at that time. So now let's go. Now that I've just showed you a few things about moisture, let's look at a little more in depth, we'll say, about all of moisture. So how does the cycling of water in the atmosphere system work? Well, we have things called atmospheric. I showed you a couple of them today. The one coming off the east coast of the United States, the one coming into the Pacific Northwest. Both are atmospheric rivers. They can travel long distances and pull tons of moisture in from the oceans. And these rivers of moisture literally rise up with fronts. They might rise up with terrain. I'll give you a classic example of terrain that applies in West Virginia. Say I have a large storm coming up east of the Appalachian Mountains, pulling up a lot of moisture. Now, on the east side of the mountains, the air is being lifted as it's coming in. Remember, counterclockwise flow. So as it's coming in, it's lifting the air. Guess what? Most of that rain, the heavier rain, will be on the eastern slopes of the mountain. You'll get some rain or snow on the western side, but not as heavy as on the eastern side. Now, move that low to the north. Now we go off, say we have winds coming out of the off the Great Lakes. Great Lakes don't have as much precip, but which way are they moving into the mountains? They're coming in from the west, right? Which side of the mountains are going to get this? Basically usually snow with lake effect snow? They're going to be on the west side of the mountains. So depending on the wind direction, the more snow or precipitation is going to occur on which side of the mountains we're looking at. So topography can play a huge role in where your precipitation occurs. So here is a typical global water cycle. Talked a little bit about that this week because you want to know where your moisture is coming from, right? Well, a lot of it evaporates over the ocean. Some of it evaporates over lakes, hits the clouds, condenses, and moves with the atmospheric flow. Maybe it hits a mountain and snows. Maybe it will hit a cold front or a warm front and rain or snow or a low pressure system. Then that rain may happen over the ocean and it just goes back in to feed the ocean. Or it might happen over a mountain or a flat land. Well, I know from experience in West Virginia, for example, that when it hits the mountains, that rain is going to come down the sides of that mountain very quickly. The water will just flow down the side of the mountain to the valley area very quickly. Now, by the same token, if I hit a flat area, and I live in a fairly flat area here in southeastern Virginia, that water is not flowing anywhere. It is just sitting there on the ground, waiting for something to move it. Or, in like cases like where I live, it's going to eventually go into the soil. However, on a mountain slope, it's going to move away quickly. And guess what? Think about a city. A city is almost all concrete, asphalt. It doesn't let that water go into the ground. So if it does that, what happens to the water? Well, it's got to go through a drainage system developed by the people that built the city. And maybe that drainage system is wonderful and really can take all the water away. Or maybe like can happen in some places. We just get a little too much water for that drainage system. And drainage systems are designed differently for different parts of this country. For example, where you get more rainfall in the east or south, that drainage system has to be designed to have, usually they look at 100-year rainfall events. So it can hold a lot more water coming in. Now, I was out in Tucson the other few years ago for a conference, and we had a thunderstorm. We only had a half-inch of rain. That half-inch of rain flooded large sections of Tucson. Why did it flood it? Tucson doesn't get that much rain. So their drainage system was totally set up completely different than what further east. All right, so water changes phase. It's the only thing in the atmosphere that does. So we know about evaporation, condensation. Transpiration is just water being taken up by plant root. Sublimation. Here is one a few of you all missed. Guess what? Water vapor can develop out of ice or snow. So you go directly from a solid to a gas, or you can go from a vapor, such as water vapor, and you see ice crystals, frost on the ground. That's deposition. Humidity describes the amount of water vapor in the air, and it's constantly varying. So how the heck do we measure it? Well, guess what? We measure it, and we want to know this by vapor pressure or mixing ratio, precipitable water, all different things. Well, vapor pressure, we've been talking about atmospheric pressure. So the vapor pressure of water, the higher that value would be, the more water would be in the air. The lower that value is, the less water is in the air. And guess what? If you take the volume in the lowest kilometer of the atmosphere, where most of the liquid is, most of the water vapor is, that can make up maybe up to 4% of the atmosphere's mass. Not a very big amount. So mixing ratio, we're basically counting up mass, so molecules or whatever of water. So mixing ratio is the mass of water vapor compared to the dry air. So if I have a whole big quantity of air that has one mixing ratio, one amount of mass, pull out water vapor, and then compare it to what's left, that's the mixing ratio. Specific humidity just adds that water vapor back into that mass. So there's a slight difference in the values. Now, with that, saturation. Air can only hold so much water vapor before it has to condense that water. It just can't hold anymore. That's the point of saturation. It's when literally liquid water and vapor are literally evaporation and condensation are equal. They're both happening at the same amount. You're winding up with cloud cover. So with that, every one of the terms, vapor pressure, mixing ratio, if I put saturation in front of them, we've reached that state where we're going between water vapor and liquid at the same rate. Here's an interesting curve, and you're going to want to think about this. The saturation vapor pressure. And you see how it really goes up as temperatures go up. Well, however, around freezing, where the transition is over liquid, and the molecules move more in a liquid than in a solid, saturation vapor pressure is always higher than ice. A little bit, but it's always occurring because of the motion of the molecules. It's not as much in a solid as it is in a liquid. Now, I want you to just take a look here a minute. Say you have a really hot day, 35, 40 degrees Celsius, 104, 76.78 millibars of air pressure you could have. Now, and that would be saturation. Now, let's go in the wintertime. 32 degrees, 6.11, 1/10. So in the wintertime, you're not going to have as much moisture in the air as you do in the summertime. Relative humidity is basically measuring how close to saturation the air is. I am real interested in that. If I live in a valley in West Virginia, for example, I want to know when fog's going to occur. And there's a lot of fog in West Virginia valleys. I've learned through the years. And with that in mind, I can look at the relative humidity and see how close the vapor pressure is to the saturation vapor pressure. The closer they are to each other, the higher the relative humidity until it reaches 100%. And at that point, I am getting fog probably, or dew. So we know now the temperature, the higher the temperature is, the more the air can hold. Well, since moisture is probably not changing a whole lot, a lot of days, you're going to get your highest relative humidities in the morning when the temperature is coldest, and your lowest relative humidities in the afternoon when the temperatures are warmest. So that's why the relative humidity curve, if you plot it, looks exactly opposite of your temperature curve. Here, for example, is the dew points in the winter versus summer. Notice in winter, average dew points are fairly, it's cold. 20 to 30, maybe even less. In the summertime, notice how they really go up a lot, much higher, especially in the south where all the moisture is feeding up and into the plains here. Notice some of these higher dew points over here. Well, guess what? A lot of that is because of plants. It's a lot of agriculture going on out there. And where the agriculture grows, plants grow. Where they're growing, you wind up with evapotranspiration or transpiration, and it goes up into the atmosphere. It literally raises the dew points because you get extra moisture from the plants feeding out the moisture from the ground. So how does the air become saturated? Well, there's got to be a way to cool air, right? We know that air rises, so that is where the air is going to begin to be cooled when it rises, and that's when we know the temperature is going to drop. Temperature drops, can't hold as much moisture, saturation. You can advect moisture in and make it saturated. When I was at a football game at Florida State, I was watching a high school game. And in off the Gulf of Mexico started this stream of moisture. And it started creating fog because the temperature was just slightly cooler over the land than it was over the ocean, the Gulf at that time. And that literally, the moisture kept feeding in, fog kept getting thicker and thicker till by halftime you couldn't see across the field. All right, the last part we're going to talk about a little bit here is stability. You need to understand stability because the atmosphere with stability makes a huge difference in the amount of clouds, the strength the rain may occur, how heavy the rain may be or the snow may be, or maybe it'll become sunny. All right. We talked a little bit about air denser. We're going to talk about a concept of an air parcel. I don't care what size of an air parcel. Think of it as a big balloon if you want, or a couple 100 meters across, or even a half mile across, whatever you want to call it. A half mile by half mile by half mile for all I care. In that parcel of air is one temperature. Outside of it, at this moment in time, same temperature. Now, the air outside it cools at a certain rate. We'll say it's cooling maybe 8 degrees for 1,000 meters. Well, that air parcel is now rising up. What's happened to it? It's cooling at the same rate as the dry adiabatic air. So in 1,000 meters up, it's cooled 9.8 degrees Celsius. Hold it. That is 1.8 degrees Celsius colder than the environment. That air parcel is now 1.8 degrees colder than the environment means it's more dense through night because colder, and things that are denser than surrounding will tend to sink. So that is a stable air parcel because that air parcel is going to want to go back down, get compressed to where it's the same temperature as the environment. So that is one way of looking at that air parcel. Now, let's take a look at that same air parcel. It's cooling at 9.8. Oh yeah, there's a certain amount of moisture in that air parcel now. It reaches saturation. Now, how fast is that air parcel cooling? Oh, it might be only cooling about 6 degrees. So, where it was stable in the first 1,000 meters till it hit that condensate, till it hit the point where it was saturated, now in the next 1,000 meters up, it's only cooled 6 degrees while the surrounding air cooled 8. All of a sudden, it's 2 degrees warmer than the surrounding air. It's less dense. It wants to take off and fly upwards faster and faster. It's going to accelerate up. That's unstable air. So that is where air becomes unstable, typically when it becomes saturated and condensation occurs. It doesn't always happen. It depends on the air parcel temperatures around it. So that's called conditional instability, is what I just described. And think about it, there's all kinds of lifting mechanisms. Convection is one. We see the cumulus clouds out there, or the sun heats over a parking lot or over a big area grass or something. Maybe a mountaintop. It heats the mountain before it heats the valley, and that air starts to rise up the hill. You can also get fronts to cause air to rise, low pressure systems. All of that causes air parcels to rise. Once an air parcel reaches a level where it becomes saturated, that's called the lifting condensation level. And at that level, clouds will begin to form. And where the clouds begin to form, temperatures change. You might get in unstable air. You might not, but you might. If you do get unstable air, the air is going to tend to fly upwards faster than even the normal speed it was being pushed up the hillside. If it's going up faster, it just means the air is going to get lifted more, where it's even colder than it was before, and you wind up getting even heavier and heavier precipitation. Mountains, I talked about rain shadows and all that. So I hope you got a little bit out of this. Let me know if you have any questions about this at all.